The third of the primary converter is the buck boost converter. It can do both operations. It can do buck operation and also boost operations depending upon the value of the duty cycle or the duty ratio. Now let us draw the circuit. You have the input voltage source, single pole double throw switch connected like this. In the case the buck converter, the inductor was on the output side. In the case the boost converter, the inductor was on the input side. In the case the buck boost converter, the inductor is in the middle, connected down to the ground. Then you have the capacitor connected across the output in this fashion and R0. So this is Vi, this is R0, this is V0 measured in this fashion, and Vi measured in this fashion. You have the pole, this throw 1, throw 2, C and L. Now during DTS period, let us say the pole is connected to T1. So let us say we connect it like that. So which means the current will flow in this path, current flows in this path and charges up the inductor. Now during the 1 minus DTS period, the pole is connected to T2 in this fashion. The inductor current should continue to flow, but it cannot flow in the input path because T1 throw is open now. So it has to continue to flow in this path, take this direction and come back and join and freewheel in this fashion. So the inductor current continues to flow, but when it is flowing through the capacitor, look at the direction. The charge on the capacitor will be plus minus in this fashion, which means you will have a negative voltage. V0 will be negative and I0 will be flowing in this path, in this direction. So that is one difference that you would find in the buck boost converter with respect to the buck and the boost topology. So this freewheeling action which causes the output voltage to develop is called the flyback action, and in the isolated version we call the buck boost converter, isolated buck boost converter as the flyback converter. So anyway, let us now try to understand this buck boost converter with waveforms and try to find out what are the values of L and C and also the type of switches that you will use for the single pole double throw switch. Let us now try to understand the operation of the buck boost converter with the help of waveforms, typical and important waveforms. We have here the single pole double throw switch. P is connected to T1 for a period of time DTS. P is connected to T2 for a period of time 1 minus DTS. We will measure the voltage across the inductor VL in this fashion. Common point here, measuring probe point here. I0 is as indicated here in this direction. IC is in this direction as we explained. IL current waveform, and now we shall plot the important parameters and try to understand the operation of the buck boost converter. Like before, I will divide the time axis into 4 segments. DTS, 1 minus DTS, DTS and 1 minus DTS together they make up TS, that is one switching period. Likewise, I have 2 switching periods here for the waveforms, and let us plot first the voltage across the inductor. So we will plot VL, and during DTS time, what is the voltage across? During DTS, the pole is connected to throw 1 and the entire Vi is coming across the inductance. Pole is having the same voltage as Vi. So this will be Vi. And during the time 1 minus dTs, the pole is connected to T2, and therefore T2 potential, which is actually minus V0 here, minus V0 comes directly across L. So therefore you will see V0 coming directly across L, and we have seen that the charge on the capacitor is reversed, plus minus in this direction, because the current is flowing like that to complete the inductor freewheeling current path, and therefore V0 measured in this fashion with a common here and the measuring probe here will show a negative voltage value. So that is V0, which is minus. And then again next cycle, Vi here, V0 here, and so on and so forth. It continues. So this is the inductor voltage waveform. Remember to use this for the volt-second balance equation to obtain the input-output voltage relationship. Next, let us look at the current through the inductor IL. So that is another next important waveform that we need to look and understand. So the inductor current will have an average value. So this is the average value which I am indicating, and for now I will call this as IL average, because it is neither connected to the input nor to the output. In fact, it is connected to both for parts of the time, and therefore we will see what it is later. For now, call it as IL average. This is the steady DC portion. On top of it, there will be the ripple portion. Now the ripple portion, as before, I am drawing a straight line because the voltage across the inductor is fixed constant Vi during the DTS period. So there is going to be a delta IL change with a fixed slope, fixed rate, and that is Vi by L. And then during the 1 minus dTs period, it is going to fall because the inductor is going to discharge into the load at a constant voltage being applied across the inductor, which is minus V0. We see that there is a minus V0 applied here. So there is a minus V0 by L, and that is the falling slope. And so on it continues again for the next positive and the next negative discharge portion of the inductor current. Next, let us have a look at current through T1P. T1P current. The current through T1P. The current through T1P should be that part of the inductor current that flows through the input source when P is connected to T1 during DTS period, and that will be the DTS portion of the inductor current. So we can draw the DTS portion of the inductor current. 1 minus DTS portion will not flow through the input source because T1 is open. So there is no current flow during 1 minus DTS period. Again, the next DTS period, you will have the inductor current flowing through the input source. So T1P will have a current like the inductor current, but only the DTS period part. Now this has an average. So this is the current. This IT1P is the current that is flowing here, and we'll call that one as II. And II, the average II current will be the average of this wave shape. So this average is II average, you can call it as that. Next, let us look at current T2P. The direction of the current through the inductor cannot change. So what was T1P now becomes T2P, the inductor freewheeling in this fashion. And T2 is connected to P during 1 minus dTs period. So that portion of the inductor current that occurs during 1 minus dTs period will flow through T2P. So during DTS period, T2P will show 0 current. Then it will show the inductor portion of the current passing through T2P during 1 minus DTS period, again DTS period 0, and so on. So this will have an average. Now this current, the same current flowing here also, splits in two parts, IC and I0. IC is the zero average part and the average part flows through the load. So the average part is nothing but I0. Looking at the figure, you can see that the average part has to be I0 and the non-average part flows through IC. So in effect, if I remove this average part, bring down this waveform to zero average, I will get the current through C, that is IC. So if I do that exercise, I will see that I will be bringing down, removing the average part, bringing down the waveform by I0. So this amount which it has come down is equal to I0. Now this current wave shape, waveform will have zero average because the current through the capacitance has to be zero average under steady state conditions. So these are the various waveforms, the various voltages and currents that you will see in the buck boost converter. Let us now find the input output voltage relationship and the input output current relationship for the buck boost converter. So first the input output voltage relation. Let us use the voltage across the inductor wave shape, the voltage across the inductor, and apply the volt second balance for the voltage waveform. So this is the portion of the waveform, inductor voltage waveform above the zero line, and this is the portion of the inductor waveform below the zero line. The area under this portion of the curve and area under this portion of the curve should cancel out and balance each other out in the steady state. So that is what we will be doing, applying the volt second balance. So let us consider this area, the volt is Vi, second is DTS, plus take this portion of the area during 1 minus DTS period is V0 into 1 minus DTS should be 0. So this is the volt second balance equation. I will remove this variable and rearranging, you have V0 is equal to minus VID by 1 minus D. So this is the input output voltage relationship. Observe the negative sign because of the direction of the measurement here, and because the capacitor charges in reverse here, you will see the negative sign appearing. If you chose the direction of measurement in the opposite direction, this will become a positive one. Anyway, we are bothered about the magnitude of the conversion. So V0, which is equal to VID by 1 minus D. So if you look here, the absolute value, only the magnitude of the V0 I am considering, is less than Vi, it's the buck operation, for the value of D 0 to 0.5. So between 0 and 0.5, when the value of D is less than 0.5, you will see that this is less than 1 and therefore it is attenuation or buck operation. V0 is equal to Vi for D is equal to 0.5. 0.5, you will see the attenuation factor here is 1 and therefore V0 is Vi by magnitude. And V0 is greater than Vi for D between 0.5 and 1, during which time this ratio becomes greater than 1 and therefore it is boost operation. Therefore, you see that this converter operates in buck mode for D less than 0.5 and in boost mode for D greater than 0.5, and therefore it is called the buck boost converter. Let us now find out the input output current relationship. So let me move this up a bit. So the input output current relationship, you can use the amp second balance but much simpler to use the power balance. Pi is equal to P naught. VI I average is equal to V naught I naught. I naught is the average on the output side, and therefore I am taking the average on the input side because the input current is switched. Therefore, I am taking to take the relationship of I average with I naught. I naught is also an average. And now this portion, let me replace it with this equation. I will use that equation from the old second balance relation. Vi into II average is equal to, I will only bother about the magnitude. So Vi d by 1 minus d into I naught. So let me remove these two parts, Vi and Vi, and simplifying you get II average is equal to I naught into d by 1 minus d, and this is the input output current relationship for the buck boost converter. Let us now try to find the values of the components, inductor first, then capacitor, and then we will try to identify the switches and the ratings. So first the inductor L. So let us look at the inductor current waveform. We see that the inductor has a change, delta IL, I'll call that delta IL like before, in time dts, and another delta IL change during the 1 minus dts period. So we can use the Faraday's law where V is equal to L di by dt or di by dt is equal to V by L. So delta IL change during dts time period, and the slope is Vi by L. Or I can use delta IL change during 1 minus dts period with the slope V naught by L. So I am only taking the magnitude because we want to find L, which is always positive. So using this equation, I will use this equation because it has just only V naught, and V naught is the regulated voltage rather than Vi, and therefore from this you have V naught. I will retain L, I will push it on this side, delta IL will come in the bottom, 1 minus d will come here, and Ts which was here, 1 by Ts is Fs, I will put Fs in the denominator. So this way you simplify, you get the relationship for the inductor value L. So this is the basis for the inductor value design. All values are known. V naught is coming from the output specification, D is coming from the input output voltage relationship because input is specified, output V naught is specified, D can be found out. Fs is the designer parameter. Designer will choose what is the frequency of operation of the switches for the buck boost converter, and delta IL as before you take it as 10% of whatever this IL average is. But just look at the other two waveforms, IT1P and IT2P. IL average is nothing but II average plus I naught, which is the average of IT2P. The IL average is equal to IT1P current waveform average, which is II average, plus IT2P average, which is I naught, because these two sum up to give you IL. II average from the input output current relationship we know is I naught into d by 1 minus d plus I naught, which works out to I naught by 1 minus d. So this is IL average, and therefore this IL average is I naught by 1 minus d. So this also you can estimate from the specified parameters. I naught you know from the max power that needs to be delivered, that is a specification, output specification. D is obtained from the input output voltage specifications, and therefore IL average is known, and therefore 10% of IL average is known, and you can find out the value of the inductor. Next, let us find out the capacitor value. We go again by the change in the charge in the capacitor within a cycle. We know that the area under the IC curve is the change in the charge. The area under the IC curve during 1 minus dTs period and the area under the IC curve during the dTs period should match, balance out. So let us use that idea. And it is easier to get the change in charge during dTs period because this is a rectangle of height I0 and width dTs. So let us use delta Q is equal to C delta V, and this is the delta Q, and this height is I0 into dTs will give you the area delta Q, which is C into delta V. And from here C you can find out I0 d Ts, I will take it to the denominator as Fs, and delta V comes down Fs, and this becomes the relation to obtain the value of C. I0 is known from the output spec, D is calculatable from the input output voltage relationship spec. Delta V is a spec of the output voltage ripple. Fs is the designer parameter which is chosen by the designer depending upon the frequency at which the single pole double throw switch is being operated. So using this equation you can arrive at the value of C. Let us now select the switch elements for the single pole double throw switch. Considering the switch elements now, let us find out what is the static switch requirements, static characteristic of the switch. Now we will take T1P and T2P one after the other and see how the static characteristic for the switch looks like. V T1P on the x-axis, I T1P on the y-axis. Now if you take this switch during the time dTs, when pole is connected to T1, there is a current flow. The current flow is from T1 to P, T1 to P being positive, and you see that I T1P is always positive above 0 and there is no current flow from P to T1. So therefore we can say that all the positive axis of the current are possible operating points. Then when PT1 is open, PT2 is connected, the pole voltage is at minus V0 and T1 throw voltage is at plus Vi. So throw T1 is at a higher positive potential as compared to P, and therefore T1P should support positive voltage during off condition. So therefore all these are potential operating points. Now this, if you look at the characteristic and the characteristic of typical devices, you will see that they map to BJT and MOSFETs and even IGBTs. So T1P can be replaced with a BJT. Now when you come to T2P, VT2P and IT2P are the important variables here. So during the time when T2 and P are connected, there is a current flow from T2 to P because inductor current should not change direction. So all the positive axis of current becomes potential operating points. And during the time when PT2 is off, P is connected to T1, so P is at a positive potential. T2 is connected to the output, so it is at minus V0. T2 is minus V0. P is positive potential, so T2P is a negative voltage. So the switch T2P should support negative voltage. So all these negative axis of the voltage become possible operating points, and this has a typical nature of a diode switch characteristic. So now we know that for this we need to use a diode. Let us now use the BJT for T1P and diode for T2P, replace it in place of this single pole double throw switch and see how the topology evolves. So let us erase some portion, make some space. We will put a BJT here like this. Observe the direction of the current flow is from T1 to P, and then we will make some space here and then put the diode here. Again, the direction of current flow is from T2 to P, keeping that in mind. So this is T1 and this is T2. So now you have the BJT and the diode interposed inside the circuit, and this gives you the entire buck boost converter topology with semiconductor switches. So now this is Q and this is D. Let us write down the ratings for Q and ratings for D. The VCO rating of this, when the switch is off, collector is at Vi potential and the emitter, the diode is conducting, freewheeling during that time. The emitter will be connected to minus V0. So Vi, and on this side minus V0. So the QVCO should be greater than Vi minus or minus V0 or Vi plus V0. ICM, the current through that, we see IT1P. This is the peak current, and we know this is IL average. The peak value is plus delta IL by 2. IL average we know is I0 by 1 minus D and plus delta IL by 2. So therefore ICM is I0 by 1 minus D plus delta IL by 2. The D rating, similarly, we can find out peak inverse voltage across this. When diode is off, T2 is at minus V0, pole, because Q is conducting, pole is at Vi. So the peak inverse voltage is Vi plus V0. Should be greater than that, and IDM, the peak voltage is same, peak current is same as this I0 by 1 minus D plus delta IL by 2. And you can find out from the wave shapes, current wave shapes here, the average and the RMS values also if needed.